1.1 Which of the following best illustrates balanced forces? So let's break that down before we even attempt to answer the question. When you're thinking about balanced forces, you're thinking F net is equals to MA and F net is equals to 0. Your object is stationary or it is moving at a constant velocity. That's when we can say that forces acting on an object, they are balanced. Let's look at option A. A person lifting a heavy object from the ground. Obviously, if you're lifting the object from the ground, the forces are not balanced, right? And then B, a big rock free falling to the ground. If it is free falling, there's only gravity acting on the object. Acceleration is not equals to 0. So we cannot say that the forces are balanced. And then C, a light stationary object. The object is stationary. So obviously our acceleration is equals to 0 meters per second squared. That is exactly what we're looking for. So the answer to 1.1, we can go with C. Let's look at 1.2. An 8 kg box is placed on a rough surface as shown below. If a force of 16.5 Newton is applied to the box and it accelerates at 1.5 meters per second squared to the right, the frictional force between the 8 kg box and the surface is, so again, back to the basics, F net is equals to MA. Let's sketch a free body diagram for the object real quick. So we just have the force that is applied, which is equals to 16.5 newtons, and we have some frictional force, which is what we're looking for. So if we substitute that into F net, we're going to say force applied minus frictional force is equals to MA. The force that is pulling the object minus all the forces that are opposing the motion. So that is 16.5 minus frictional force, which is equals to the mass. The mass is 8 kgs and the acceleration is 1.5. So 16.5 minus frictional force is equals to 8 multiplied by 1.5. That's supposed to give you 12. So you can see now that the frictional force will be equals to 4.5 newtons. That is because 16.5 minus something to give you 12. So that something must be 4.5 newtons, right? So that seems like our answer to 1.2 is actually B. Let's move to 1.3. 1.3, a ball is dropped from a certain height above the ground and bounces a few times as it hits the ground. The velocity time graph below describes the motion of the ball from the time it is dropped. Ignore all the effects of friction. In relation to the velocity time graph for the bouncing ball shown above, which statement below is correct? And then A is saying down is taken as positive direction. So let's look at that. Our ball is being dropped from a certain height and it starts going down. So if down was taken as positive, then our VT graph should immediately go up, but then it is immediately going up. So we're taking up as positive and down as negative, right? So option A that says down is taken as positive, we know that it is already not correct. Let's look at B. B says down is taken as positive. Again, we know that B cannot be correct because we can easily see that down is not taken as positive. Let's look at C. Down is taken as negative. Right. Now there's something to think about. Down is taken as negative and the ball is at its highest point of its bounce at C. So let's go and look at C. C is right here. C is right here. And we know fully well that at the highest point, V equals to 0 meters per second. So C cannot be our highest point because velocity is not equals to 0 at that point. Now by elimination, our only answer remaining is D. Let's look at it and see why it makes sense. Down is taken as negative, true, and the ball is at its highest position of its bounce at D. Yes, D can be our highest point because velocity at that instance, it is equals to 0 meters per second. Right, let's move to 1.4. So we have 1.4. Two identical solid spheres, each with a mass m and traveling at a speed v, move towards each other in an isolated system. The spheres have a head-on elastic collision. Which statement is correct for the collision as described above? So if collision is elastic, then the momentum EP before shall be equals to EP after, right? And then another thing that is true about an elastic collision, EK before should be equals to EK after, right? So the momentum before, because we have M multiplied by V plus M multiplied by minus V, because the other sphere, the other solid sphere, has the same mass but in the opposite direction. The momentum before is equals to 0, right? So the momentum after should also be equals to 0. Let's look at the kinetic energy. The kinetic energy before is a half M V squared plus a half M minus V squared, which is just going to give us, this will give us a half mv squared plus a half mv squared. So this is just mv squared. This is the kinetic energy before and the kinetic energy after. This is the momentum before and the momentum after. Let's look at our options. Option A is saying the spheres stick together on impact. We're not really sure. And then B says, let me not say A here because it seems like I'm saying A is the answer. And B says the total kinetic energy after impact is mv squared. Yes, that's what we have. The total kinetic energy before and after is mv squared. So 1.4, we don't even have to go through the other options. Our answer is B. We have proved that beyond reasonable doubt. 1.5, the mechanical energy of a moving object will remain constant if its free body diagram looks like this. If this is the free body diagram of the object, then the mechanical energy will remain constant. It will be conserved, so to say. So A, there are frictional forces present. If there are frictional forces, your free body diagram will not look like this. And then there is only gravitational force acting on it. We don't have to go any further. The answer is B. Mechanical energy is conserved when your free body diagram looks like this, right? 1.6. A train is moving at a constant velocity of 10 meters per second while sounding its whistle, which has a frequency of 500 hertz. Take the speed of sound in air as 340 meters per second. What frequency will be heard by a man sitting in the train? So when the man is sitting on the train, the man and the train have the same velocity, right? So let me just do the math real quick. So we know that FL is equals to V plus or minus VL divided by V plus or minus VS multiplied by FS. So V is the same for the man and the train. And then VL and VS, they are the same for the man and the train. So basically we have FL being equals to FS. So the man is going to experience the same frequency that the train is emitting because he and the train are moving at the same velocity. So 1.6, we have the answer being A. He will experience a frequency of 500 Hz, the same frequency that is being emitted by our train. 1.7, the diagram below shows a point P at a distance R from a charged sphere Q. Right, the electric field strength at point P is, let's look at A, directly proportional to R. No. It's supposed to be inversely proportional to R squared, right? Because E is equals to Q1 divided by R squared. So it's supposed to be inversely proportional to R squared, not directly proportional to R. So A is definitely not correct. Let's look at B, directly proportional to the square. So if it says directly proportional to the distance between the two, then it is incorrect. It's supposed to be inversely. And then C, inversely proportional to the square of R and to the right. And then D, inversely proportional to the square of R and to the left. Right, so now we just need to look at whether it is to the right or to the left. It is indeed inversely proportional to the square of R, as we can see from our formula. So now we have to be asking ourselves, Q is negatively charged. Where do the field lines point on a negative charged sphere? They point towards itself. The field line will point towards the charge itself. So you can see here that at P, the field lines will be pointing to the left. They will be pointing towards Q, right? So the answer here to 1.7 is supposed to be the field lines at P will be pointing to the left. They will be pointing towards Q, as you can see from the field lines that surrounds Q as a negatively charged sphere. So inversely proportional to the square of R and to the left. That is option D. 1.8. 1.8 is saying which of the following statement about the AC generator is true. The minimum potential difference produced is not 0 volts. It is 0 volts. So that cannot be our answer. B, the EMF produced decreases as the number of windings increases. That is not true. That is not true. We know from grade 11 that if you want to increase the EMF induced, you can increase the number of turns. You can increase the number of windings. So B cannot be correct. The maximum value of the AC can be increased by increasing the period of rotation. Well, I was initially conflicted between C and D. And then I realized that increasing the period of rotation is decreasing the time it takes for one cycle to be completed, because period is the time it takes to complete one cycle. So if you increase the period, it means that you are now rotating very slowly, and that cannot increase the EMF. So by elimination, it seems like our answer is D. It also makes sense. The maximum value of the AC produced can be increased by increasing the speed of rotation of the coil. So 1.8 is our correct answer. Let's look at 1.9. 1.9 says that a battery with internal resistance is connected to a fixed resistor R. A voltmeter is connected across the battery, as in diagram A. The battery is replaced by one with the same EMF but with a larger internal resistance, as shown in the diagram. In diagram B, how will the voltmeter reading and current through the fixed resistor change compared to diagram A when switch S is closed? So EMF is equals to V external plus the current multiplied by the internal resistance. The EMF is staying the same. Our battery still have the same EMF, but then now it has more internal resistance. So let's look at what is going to happen. If you increase the internal resistance, the total resistance of the circuit is going to increase, and then the current is going to decrease. If the current is going to decrease and the external resistance of the circuit is still the same, then V external will also decrease, because R is remaining the same, the external resistance of the circuit. So let's look at what we have. A, with regards to the voltmeter reading, is saying that the voltmeter reading is going to decrease. Yes, the voltmeter reading is going to decrease, even though the EMF is the same. They're saying that switch S is closed. When switch S is closed, current is flowing in our circuit. So the voltmeter connected across the ends of our battery will be reading V external and no longer EMF. You need to realize that. So we're looking for answers with a voltmeter reading that is saying decreases and decreases. So now our answer can only be A or B. Let's look at the current through resistor. We have already deduced that the current will decrease, the current of the entire circuit, because it's all the same everywhere. In this instance, we don't have any resistors in parallel. So the current is also going to decrease. So that is option A. So our answer to 1.9 is A. And 1.10, this question actually doesn't make sense. The diagram below shows the kinetic energy versus frequency of a photocell that has a sodium metal cathode. The work function of sodium is 4.41 times 10 to the minus 19 joules. Let's just stay there. And then the question is saying the threshold frequency of sodium is, so we are given the work function, which is equal to Planck constant multiplied by threshold frequency. We have work function with Planck's constant. So the threshold frequency should just be work function divided by threshold, not threshold, but Planck's constant, right? And then I think, let me just look at the answer again. When you put that in your calculator, you're going to get 6.61 times 10 to the power 14. hertz. That is your answer when you use this information. And then we are given a graph. In our graph, the frequency where you start seeing some kinetic energy is given as the threshold frequency is equals to 3 multiplied by 10 to the power 14 hertz, right? So on the same equation, we have two possible answers: 3 times 10 to the power 14 hertz and 6.61 times 10 to the power 14. Well, if you look at our option, we have 3 times 10 to the power 14 hertz as option B, right? Option C is in joules, so it cannot be correct. And option D is also in joules, so it cannot be correct. And then option A is also not correct, because our answer when we use the work function is 6.61 times 10 to the power 14 and not 4.41. Unless I'm missing something. I think we actually cannot answer this question. There is two possible answers. Only one is in the options provided. So if push comes to shove, you would have to choose the option that is there on your or on one of your options. Please just let me know what you think about this question. Yeah, because I think it is very problematic. This question looks interesting, right? Let's take a look at it and see where we end up. A group of learners design a device that consists of a line to ball on a string hanging from the roof of a cargo truck. This device is used to determine the acceleration of the truck. When the truck is stationary or moving at a constant speed, the ball will hang straight down. But when it is undergoing a constant acceleration, the ball hangs down at an angle theta, as shown in the diagram below. And the first question, 2.1, draw a free body diagram of all the forces acting on the ball for 2 marks. So if this question was for 3 marks, you would expect 3 forces on your free body diagram. If it was for 4 marks, you would expect 4 forces acting on your object. And then now that it is for 2 marks, we are only expecting 2 forces to be acting on the ball, right? So let's go ahead and identify those forces. The first force, obviously, it's always weight. Before you start thinking about any other force, you put weight first, and then you go through your situation. Here we also have the tension, the reason why our ball is hanging from the cargo, right? From the roof of the cargo. So to show the tension at an angle, there we have it. We have the tension and the weight. Why am I choosing to show the tension at an angle? Because in the diagram given, the ball is at an angle 2.2, 2.2.1. In this case, the mass of the ball is 50 grams and the angle theta is 18 degrees. Calculate the horizontal force on the ball. So horizontal force on the ball, the force along the x-axis is what we're looking for, right? Let's resolve that free body diagram first. We have the weight and we have Ty, the y component of the tension, and we have Tx. In this equation, we are looking for Tx, but we don't have the tension. Although we have the angle, we don't have the tension, right? So we cannot calculate Tx directly. What we can do, we can calculate the weight and equate it to Ty. And then after finding Ty, we can then find Tx. So we're going to say that the y component of our tension is equals to the weight. Our object is not moving upwards or downwards, so this equation should be true. So to find the y component of the tension, we're going to say tension, this angle here is 18 degrees. If this angle is 18 degrees, this angle here should be 72 degrees, because this angle here is 90 degrees. So we're gonna say tension sine of 72 degrees is equals to the weight. Our object weighs 50 grams, so that will be 50 divided by 1000 multiplied by gravity, right? Gravitational acceleration, which is 9.8. It's easy to see now that we're going to divide both sides by sine of 72. So divided by sine of 72, And then we do the same thing on the right hand side. We have to divide by sine of 72. And if you do that, you should get the tension being equals to 0.5152 newtons. So that is the entire tension. We are only interested on the x component. So now we're going to see that Tx is equals to the tension cos of theta. So what is our tension? We know that it is 0.5152 cos of 72 degrees. And if you put that in your calculator, you should get 0.1592 newtons. So there we go. We have the horizontal force acting on the pole. 2.2.2 magnitude of the acceleration of the track. As soon as I start hearing about acceleration, I'm thinking F net is equals to ma. We want the horizontal acceleration. There's only one force acting on the horizontal, which is Tx. So we're going to have Tx being equals to the mass multiplied by the acceleration. Tx is 0.1592. The mass is 50 divided by 1000 multiplied by the acceleration. So you can see here that we're just dividing both sides by 50 divided by 1000, and then we do the same thing on the left hand side, 50 divided by 1000. And if you put that in your calculator, you shall get an acceleration of 3.1842 meters per second squared. 2.3. A and B below are two identical blocks, each with a mass of 5 kgs, joined together by a light inextensible string. The blocks are being pulled with a force of 65 newtons at an angle of 40 degrees to the horizontal. As we can see, the two blocks accelerate to the right at an acceleration of 2.17 meters per second squared, and the tension in the rope is 26 newtons. Right, and then 2.3.1. Let's look at what the question says. Calculate the friction on each block. Let's start with block A. Right, so we don't have the coefficient of friction, so we cannot use Fr is equal to the coefficient multiplied by the normal force. That is not going to work because we don't have the coefficient. What we can do instead is say that F net is equal to ma. So now we put in our tension on block A. So which forces are acting on block A? We have the tension, which is pulling it to the right, and then we have the frictional force, which is opposing, the normal, and the weight, which we're not interested in, but anyway, yeah, they are acting on our object. So we're gonna have the tension minus the frictional force being equals to the mass multiplied by the acceleration. The force that is pulling the object minus all the forces that are opposing is equals to ma. So what is the tension? The tension is 26, and then minus frictional force. The mass of the object is 5 kgs, and the acceleration is said to be 2.17. So minus frictional force is equals to 5 multiplied by 2.17 minus 26. So the frictional force acting on object A will be equals to 15.15 newtons. Right, that is the frictional force acting on block A. And moving to block B, let's use the same approach. Let's start with the free body diagram. We can never go wrong with the free body diagram. So we have the weight, we have the normal force, we have the tension, and the frictional force opposing. And then the force that is pulling, we have Fx, right? The x component of F. And then we have Fy, the y component of F. But we are only interested on the x component of F, right? Again, F net is still equals to ma. What do you do at this step? You say that the force that is pulling the object minus all the forces that are opposing. Which force is pulling the object? That is Fx minus all the forces that are opposing. The tension and the friction force being equals to Ma. So to find the Fx, we're going to say 65 multiplied by cos of 40. That is how we find the x component of that force. Minus the tension, which is 26, minus frictional force, which we're interested in, is equals to Ma. Our mass is 5 kgs and our acceleration is 2.17. So we're going to say minus frictional force is equals to 5 multiplied by 2.17 plus 26 minus 65 multiplied by cos of 40. Then you just put that in your calculator and it is easy to see that the frictional force acting on object B is 12.94 newtons. An object that moves under the influence of the gravitational force only. That is the definition of projectile. If you omit the word object in your definition, you lose a mark. And after gravitational force, if you omit the word only, you lose another mark. So we have to be very precise with our definitions. That is the answer to 3.1. Let's look at our question statement and try answering 3.2. So a 50 grams ball is dropped from a certain height. The velocity time graph below represents the motion of the ball as it bounces vertically on a concrete floor. The time of contact during the bounce is 0.02 seconds. Ignore all effects of a friction. And then 3.2, the question says that let's write down the magnitude of the velocity with which the ball leaves the ground after bouncing. So let's look at our graph. Our ball is dropped from a certain height with this velocity right here, which is equals to 0. And then when it strikes the ground, it is striking the ground at 3.92 meters per second. And then it spends 0.02 seconds in contact with the ground and leaves the ground with a velocity of 3.43 meters per second upwards. So the answer to 3.2, we're looking for the magnitude of the velocity with which the ball leaves the ground after bouncing. That should be 3.43 meters per second. And 3.3, draw a labeled free body diagram showing all the forces acting on the ball at 0.77 seconds. So let's go to 0.7 seconds and see what is happening. So at 0.77 seconds, our velocity is equals to 0. We know that we are at a maximum height. But apart from the velocity being equals to 0, there is nothing special about maximum height. Gravitational force is still acting on the object. It is still 9.8 meters per second squared downwards. So our free body diagram should look something like this. We have FG, right? And that is all that we are required to do for 3.3. Now let's move to 3.4 and look at 3.4.1. Use the information given on the graph and calculate the acceleration of the ball. So 3.4.1, we're looking for the acceleration of the ball. There's two ways we can use to answer this question. We can use equations of motion because we have VI, we have VF, and we have delta T. Another way we can find the gradient of our graph. The gradient of the VT graph will give you acceleration, and then the area will give you the displacement. So if we use equations of motion, our VI is equals to 0 meters per second because our ball was dropped, and VF is equals to 3.92 meters per second, the velocity at which we strike the ground. Then the acceleration is what we're interested in, and the time for that motion is 0.4. So if we use equations of motion, we're going to have Vf being equals to Vi plus A delta T. We're saying that Vf is 3.92 and Vi is 0 because it is dropped, right? Plus A multiplied by 0.4. It's easy to see now that A is just equals to 3.92 divided by 0.4, of which if you put in your calculator, you're gonna get 9.8 meters per second squared. So that is our acceleration using equations of motion. If we decide to use the gradient, we can take this first point here, we can take this point and this point and find the gradient between the 2 points, of which we're gonna get y2 minus y1 divided by x2 minus x1. y2, that is 3.92 and y1 is 0. x2, that is 0.4 and x1 is 0. Again, you can see that we're going to get 9.8 meters per second squared, regardless of which technique we decide to use. 3.4.2. The question is saying that let's calculate the height from which the ball was dropped. Again, two ways of answering the question: equations of motion or the area under the graph. For the position or for the displacement, we need the area under the graph. So also to find the height, we're going to use the area under the graph. For the acceleration, we use the gradient of the VT. So you need to know which to use when. We don't just calculate the gradient all the time, right? So if we use the area under the graph, we're going to have area being equals to half base multiplied by height. So the area which we're interested in, let me just erase this. The area which we're interested in is this very area here, is this area we have here. So if we decide to use that area, our base is 0.4. So we have a base of 0.4 and our height is 3.92. Our height is 3.92. The height of our triangle is 3.92. And then if you punch that in your calculator, you should get an area of 0.784. So our answer here will be 0.784 meters. That is the height from which our ball was dropped. Light work. Obviously, you can use equations of motions again to answer these questions. There's multiple ways of solving this one. I think there's probably 5 ways you can use to answer this question. The next question, 3.5. On the same set of axes, draw a position time graph for the motion of the ball from 0 second to 1.12 second. Use the ground as 0 reference, indicate the height from which the ball was dropped and all the relevant times on the t-axis of your graph. So let's go ahead and try that. What do we need? We need our set of axes. We need a set of axes. So our y and our x. We are good to go now. We can say that this is y in meters and this is time in seconds. So our maximum height where our ball was dropped, that is 0.784, and we strike the ground after 0.4 second. We're in contact with the ground for 0.02, so we leave the ground at 0.042 seconds. So let's just plot that first before we carry on. So if we connect those two, we should have something like this. And then our ball will leave the ground. Obviously, it reaches another maximum height. We can see that from our velocity time graph, right? It reaches another maximum height, and then it goes down to strike the ground again. So there at the maximum height, we have a time which is 0.77 seconds. Here it is right here. And then the entire time for the motion is 1.12 seconds. And I think we get to go. I think we've indicated all that we needed to indicate. Let's look at 3.6. Give one term for the rate of change of momentum. One term for the rate of change of momentum. What's happening here? So the rate of change of momentum, delta P divided by delta T. We know fully well that this is equals to F net. So the one term which we should give is net force. Net force, right? If not net force, then at least resultant force. Yeah, there isn't anything else we can say there. 3.7. Calculate the magnitude of the force exerted by the floor on the ball for the time of contact. So let's go to a graph and look at that. Yeah, let's just erase this. So we're interested on only this part of our motion. We're looking for the force that the floor exerts on the ball. But let's just sketch or draw the free body diagram of the ball while it is in contact with the floor, so that we can have a bit of clarity. So if we do that, we're gonna have FG, obviously, as always, and then the floor is gonna be pushing the ball upwards. So this will be the force exerted by the floor. So that's what we have there. That is our free body diagram. So we can say that F net is equals to F exerted by the floor minus FG, because they are in the opposite direction. So if we calculate F net and we find another way of calculating FG, then we essentially have the force that is exerted by the floor. How can we find F net? We know that F net is equals to the change in P divided by the change in T. So at 0.4, we start with a velocity of 3.92. And at 0.42, when we leave the ground, we have a velocity of 3.43. Now it is important to note that it is 3.92 downwards, and then it is 3.43 upwards. So that will be essential when we choose which direction we take in as positive and which direction we take in as negative. And obviously our change in time is 0.02 seconds. So that seems like we have F net covered. We know that the mass is equals to 50 grams. So we have F net covered. FG, we also have it covered, because you know that FG is our utmost simple case, right? So FG, the mass is 50 grams, and the gravitational acceleration due to the Earth is 9.8 meters per second squared downwards, right? That direction is going to come in handy when we substitute. So which direction do we want to take as positive? Let's take up as positive. So take up as positive. Take up as positive. It is just common sense. So in place of F net, let me just write our equation down again. So F net is equals to the force applied by the floor minus Fg. So in place of F net, we can put the rate of change in momentum, right? So the mass will be 50 divided by 1,000 multiplied by Vf, which is 3.43 upwards, minus Vi, which is 3.92 downwards. So if it is downwards, we should substitute it with the minus sign if we take it up as positive. So we're going to have minus 3.92. We close that bracket and we divide everything by 0.02. And then this will be equals to the force that is exerted by the floor minus Fg. So what is our mass? Our mass, again, we have 50 divided by 1,000 multiplied by 9,8. So that is 9,8 downwards. So it will actually be minus 9,8. Well, we have already indicated that FG is going downwards by this minus sign right here. So our 9,8, it actually doesn't need that negative sign, because if it has that negative sign, then we have the force exerted by the floor plus the force exerted by gravity, because that minus and that minus will give you a positive. So that 9,8 is actually supposed to be positive. So we have 9.8 here. And now what you are left with is taking this term to the left hand side. And if we do that, we're going to get the force exerted by the floor being equals to. So now let's just drag and drop for the sake of time. So we duplicate that, and then we're going to have plus 50 divided by 1000 multiplied by 9,8. And that should give us 18.865 newtons. Right, 3.8. In 3.8, the question is saying, if a softer ball is used and the time of contact with the floor is increased while the change in momentum remains constant, how will it influence the force on the ball? Right, only increase, decrease, or remain the same? It is going to decrease, so the answer here is decreases. Why am I saying that? We have already deduced that F net is equals to the change in momentum divided by the change in time. So we're keeping the change in momentum constant. We're saying that it is the same. If we increase the change in time, F net would decrease. Why are we saying so? F net is inversely proportional to the time of contact. Conservative force, it is a force in which the work done in moving an object between 2 points is independent of the path taken. So that is 4.1, right? If we move to 4.2, the question is saying that let's name the conservative force in the diagram above, right? Without even looking at the diagram, I know that in our context, in our scope, we have only one conservative force, which is force of gravity or gravitational force. So the answer for 4.2 is force of gravity. That's the only conservative force we talk about in our scope. Moving to 4.3 saying that let's take the work energy theorem in words. So we have work net being equals to the change in EK, and that in words goes as follows: the net work done on an object is equals to the object's change in kinetic energy. So the net work done on an object is equals to the object's change in kinetic energy. Basically, you just explaining the formula, right? Because it's easy to see from the formula that the net work done on an object is equals to the object's change in kinetic energy. 4.4. So 4.4 is in that the velocity of the block at point B is 6.92 meters per second. So at this point we have 6.92 meters per second, right, at point B. And then the question goes on to say that use energy principles only to calculate the frictional force that the block experiences and it moves from point A to point B. So when the question says let's use energy principles, there's two equations we can use. Work net is equals to the change in EK, and then work done by non-conservative forces is equals to the change in EK plus the change in EP, the potential energy, right? So I'm gonna go ahead and use the second equation to answer our problem, and then you guys can use the first one so that we can see if we end up at the same answer. So let me go ahead and do that, right? But then before I answer any question, I have to draw a free body diagram, right? So that I can see clearly what is going on. So if I go ahead and do that, so the block is going down. As it is going down, we know that there is the weight which we can resolve to weight parallel and weight perpendicular, right? And then we have the normal force, and we have the frictional force, right? So if you look at the forces acting parallel the surface, we have the frictional force and weight parallel, right? But then we know that force of gravity is conservative, right? So if I'm using the second equation, which says that the work done by non-conservative forces, then the only force I will consider is friction, right? So if I go ahead and do that, I'm gonna have frictional force multiplied by delta x multiplied by cos of theta, right? So that is supposed to be equals to the change in EK plus the change in EP, right? So if we go ahead and compute that, we're gonna get a half mvf squared minus a half mvi squared, and then plus mgh final minus mgh initial, right? And if we go ahead and substitute, friction is what we're looking for, so we're just going to have fr then, and then multiply by delta x, which is equals to 8 meters, right? The displacement of the object, and then multiply by cos of 180. When you're calculating the work done by friction, it will always be cos of 180 because it always acts in the opposite direction. And then that will be equals to a half. The mass of the object is 2 kgs. And then velocity final is here, right? We've talked about it, 6.92. So we have 6.92 squared minus a half the mass of the object, which is 2, and then velocity initial, which is 2 meters per second, right? We square that, and then we have plus mgh final. So the mass is 2 kgs. And then g, gravity, is 9.8, and then the height final. So now we have a problem. We need the height in order to use that equation, and we don't have it, right? So let's look here. We need that side. Yeah, we need the height. So what we have an angle and the hypotenuse, right? So it's easy to see that we can go ahead and say that. Let me just do it here real quick. Sine of theta is equals to the opposite, which is our height, right, divided by the hypotenuse. So we're gonna have sine of 30 being equals to the height divided by 8. So the height is equals to 8 multiplied by sine of 30, which is equals to 4. So our height is equals to 4, right? So let's go ahead and solve our problem. So here we're gonna have so the height final. So we're coming from a height of 4, right? And then we go in here at B where the height is 0. So the height final is 0, and then height initial is the one that is equals to 4, right? So we're gonna get minus 8 frictional force is equals to, and then if you compute the right hand side, you're gonna get minus 34.5136, and then if we divide both sides by minus 8, so let's just go ahead and do that. Dividing both sides by minus 8, we're gonna get the frictional force being equals to 4.31 newtons. So that is 4.4, right? Let's do 4.5 real quick. So 4.5, the question is saying that the coefficient of friction for the last horizontal stretch after point B is 0.35. So here we have a coefficient of 0.35, right? And then the question says that let's calculate the distance the block will travel before coming to a complete stop without using equations of motions. So if it is coming to a complete stop, then we know fully well that we have VF is equals to 0, right? But then that's not all we have. We also know that VI is equals to 6.92 meters per second for that part of the motion. Yeah, it was VF from point A to B, but then from point B to a complete stop, it is now VI, right? And then what else do we have? We have the coefficient, which is equals to 0.35. So let's go ahead and set up our equations and see what we can do here. So we can use work net is equals to the change in EK, and we are governed by the variables you have, right? If you have VF and VI, you're most likely going to use this equation or that other one. So we're not just choosing it in randomly, we are guided by the variables we have. So now all we have to do is draw a free body diagram for the object. You're gonna see real quick that the only force acting is frictional force, right? Because even though the weight is acting on a flat surface, it does zero work. We have the normal, it always do zero work. So we're gonna have the work net being the force done by friction multiplied by delta x multiplied by cos of theta being equals to a half mvf squared minus a half mvi squared. So frictional force, the frictional force will be the coefficient multiplied by the normal force. We know that fully well, right? So the coefficient is 0.35, and the normal force is mass multiplied by gravity, so that will be 2 multiplied by 9.8, and then we have delta x, and then the angle that we have there is obviously cos of 180, right, for frictional force, and that should be all equals to, so I'm running out of space, so I'm just gonna write it here. So that should all be equals to a half, the mass is 2 kgs, and velocity final, we know that it is 0 if we go into a complete stop, right? And then minus a half, 2 kgs, and then the initial velocity is 6.92 squared, right? So now all we need to do is just solve the right hand side and look for delta x, right? So if you do that, you're gonna get minus 6.86 multiplied by delta x is equals to the right hand side. So let me just put that in my calculator real quick and see what I get here. So I'm getting minus 47.8864, and then it is easy to see that we're going to divide both sides by minus 6.86, right? And then if we do that, we're gonna get delta x being equals to 6.98 meters. I don't think it was necessary to make the car look so animated, but it doesn't affect us with anything. Let's look at 5.1. For this investigation, write down the following: a dependent variable, one control variable, and a suitable investigative question for this experiment. So what is going on here? We have graded the 12 learners that conduct an investigation to verify the speed of a race car using the Doppler effect. So they are verifying the speed of a race car using the Doppler effect. So that's a giveaway. We have our dependent variable in that very statement, because your dependent variable is what you're measuring. You're changing something, and then when you make a measurement, that is your dependent variable. Here we're investigating to verify the speed of a race car. So our dependent variable is the speed of the race car. So that is the answer to 5.1.1. Speed of the race car. Speed of the race car. So let's continue reading and see if we can extract the control variable and the suitable investigative question for this experiment. A race car driving around a race course at a constant speed emits a single frequency of 200 Hz. A learner records the sound using a cell phone as the car approaches him and after passing him. So what will we say is our control variable in this experiment? So the answer to 5.1.2, our control variable is our speed of sound in air. Speed of sound in air, right? We need the speed of sound in air to remain constant. It's going to have an effect on our results. So we need to ensure that the speed of sound in air is controlled. How can you possibly control the speed of sound in air? It will be wise to do your experiment in a very short period of time, because if you prolong it, then the humidity will most likely change as the day progresses and your results are going to be affected. 5.1.3, a suitable investigative question for this experiment. What is the relationship between the change in the frequency that will be observed relative to the speed of the vehicle? What is the relationship between the change in the frequency that will be observed relative to the speed of the vehicle? That is 5.1. And moving to 5.2. So when playing back the sound recorded on the cell phone in the presence of an oscilloscope, a difference in frequency of 67.15 Hz was registered. Use the information above to calculate the speed of the race car. Take the speed of sound in air as 340 meters per second. So there's actually 3 ways you can use to answer this question, because it is a bit open-ended, right? You're only told that there's a difference in frequency of 67.15 Hz. Is this difference when the car is moving towards or when the car is moving away? You're not told. So you can make a calculation and solve your equation as if the car was moving towards and as if the car was moving away. And then by doing that, you're going to get different answers, which are all correct. So let's just make a calculation for when the car is moving towards, right? So we're going to have FL being equals to V plus or minus VL divided by V plus or minus VS multiplied by the frequency of the source. So there's a difference in frequency of 67.15 that was registered, right? So the frequency emitted by the source, that is 200 Hz. If we're saying that we're considering the case where the car is moving towards, then we can see FL will be equals to 200 plus the difference that was observed. And then for a person who's taking the case where the car is moving away, then it's going to be 200 minus 67.15, because you would expect the frequency observed to decrease, right? And then in our case, the frequency observed, we're expecting it to increase. So we have FS, we have FL, and we have V. It is given to us as 340 meters per second. So if we go ahead and substitute, we're going to have 267.15 being equals to 340. The velocity of the listener is stationary, right? So we can just leave that, divided by 340, and then the velocity of the source. For our case, the car is moving toward, so we're going to have minus Vs multiplied by the frequency of the source, which is 200. So we can divide both sides by 200 to get 267.15 divided by 200 is equals to 340 divided by 340 minus 4s, right? And then if you cross multiply, we're going to get 200 multiplied by 340 being equals to 267.15 multiplied by 340 minus 267.15 Vs. Obviously, we're going to take this term to the left hand side. If we do that, we're going to get 200 multiplied by 340 minus 267.15 multiplied by 340 being equals to minus 267.15 Vs. And then I can divide both sides by the coefficient of Vs, which is minus 267.15 divided by minus 267.15, right? So we're gonna get Vs being equals to 85.46 meters per second, right? If you take the case where the car is moving towards, you're gonna get something around 170 meters per second, right? So that is what is so weird about this question. Moving to 5.3, the spectrum of light from most stars contains lines corresponding to helium gas. Diagram A shows the helium spectrum as observed in a laboratory. So let's look at diagram A right there, as you can see. And then for diagram B, shows the helium spectrum of light from a distant star. And then the obvious question is the distant star moving away from or towards the Earth? Explain your answer. It is moving away. It is moving away, right? So the difficult thing about this question is that you don't know what the red end is, and you don't know where the blue end is, right? But you are given the wavelength instead, so you can deduce where the red end is and the blue end is from the wavelength, because we know that in the red end we have longer wavelengths. So right here we have the red end, longer wavelength. And then here we have the blue end, a shorter wavelength, right? We have 400 here, and here we have 700, right? And then again here we have blue, and then we have red. So here on Earth, that's our spectrum. And then here in our distant star, you can see that the spectral lines have shifted towards the red end. So it is moving away because of that. Define electric field strength at a point. This definition is actually different from electric field. So what does electric field strength at a point say? It says that the electric field at a point is the electrostatic force experienced per unit positive charge placed at that point. The electrostatic force experienced per unit positive charge placed at that point. That is electric field strength at a point. Totally different from just electric field. The answer to 6.1. Now let's look at 6.2. 6.2 is saying that let's sketch the electric field pattern around spheres B and C if A was removed. So let's look at B and C only. B is negatively charged, as you can see, and C is also negatively charged. So what is going to happen to those two spheres? They are going to repel, like charges repel. So we're going to have an electric field that looks like the following. There we go. I want you to realize something. Sphere B has a magnitude of 2.64 nanocoulombs, and sphere C has a magnitude of 7.46 nanocoulombs. That is why I'm deciding to put a lot of electric field lines on sphere C compared to sphere B. Usually examiners don't care about that, but you never know. The greater the magnitude, the more field lines you should allocate to that sphere. 6.2. Let's look at 6.3. 6.3 is saying that charge B experiences a net force of 0.004078 newtons due to charges A and C. Find the distance R between the charges B and C. Let's go ahead and do some conceptualization here. So our charge of interest is B. We have the net electrostatic force that B is experiencing due to A and C. So let's draw a free body diagram for all the forces that B is experiencing along the X, that is. So B is negatively charged, C is negatively charged. That tells us that they're going to repel, like we have deduced in 6.2. So C will be pushing B to the left. So this is F of C on B. Now let's look at B and A. B is negatively charged, A is positively charged. So A will be attracting B to the left. So again, we have F of A on B. So all our forces are pointing to the left. That is to say that the F net on B will be equals to F A on B plus F C on B. Just a friendly reminder, F is equals to K Q1 Q2 divided by R squared. So F net is equals to, actually let me not say F net anymore, because we know what F net is. F net is 0.004078, and that should be equals to F of A on B. So we're going to substitute in this formula. That will be K. K is a constant, 9 times 10 to the power 9 multiplied by Q1. So we can take Q1 as A, which is 5.6 times 10 to the minus 9 multiplied by Q2, which is B in this instance, 2.34 times 10 to the minus 9. We're only interested on the magnitude. We don't have to put a sign in electrostatics. And then the distance between them is 6 millimeters. So we're going to have 6 divided by 1,000 squared. You divide by 1,000 when you want to convert millimeters to meters. And then plus F C on B. Right. So we're going to have 0.004078 being equals to. When you put that in your calculator, you should get 0.003276 plus F C on B. So now it's just a matter of taking this term to the left hand side, and we have F of C on B, right? If you do that, you get 0.000802 being equals to F of C on B. Instead of F of C on B, now let's go ahead and substitute. So we're going to have K again, which is 9 times 10 to the power 9 multiplied by B, the magnitude of B, which is 2.34 times 10 to the minus 9 multiplied by the magnitude of C, which is 7.46 times 10 to the minus 9. Everything divided by R squared. If we do a bit of mathematical manipulation at this point, we're going to get R squared is equals to 9 times 10 to the power 9 multiplied by 2.34 times 10 to the minus 9 multiplied by 7.46 times 10 to the minus 9. Everything divided by 0.00802. We take square roots on both sides. R is equals to 0.014 meters. And just like that, we have solved 6.3. Let's look at 6.4. So 6.4, charges A and B are allowed to touch and then moved back to the original distance between them. Calculate the new charge on each sphere. So when charges are allowed to touch and then separated, we say that Q new is equals to Q1 plus Q2 divided by 2. But then in this formula, we actually have to account for whether a sphere is positively charged or negatively charged. For A, we can say that 5,6 times 10 to the minus 9 plus Q2, which is B, minus 2.34 times 10 to the minus 9 times 10 to the minus 9, right, divided by 2. The answer here should be equals to 1.63 times 10 to the minus 9 columns. 6.4.2. Explain the change, if any, to the fold pattern between B and C. So initially they were all negative, and now B, our sphere B is now positive. Our sphere B is now positive and C is still negative. So they're now going to attract. So what happens to the electric field lines when two spheres are attracting? What do they look like? the variable resistor R is set at a resistance of 3.5 ohms. So instead of having that R there, let's put 3.5 ohms. And then the first question, 7.1.1, let's calculate the total resistance of the circuit, including the battery. Right, so we're going to have RT being equals to RS plus RP. But we are required to include the resistance of the battery. So let's have plus the small r, which is our internal resistance, by the way. The resistance in series is just going to be the resistance of this variable resistor. It's the only resistor that is in series, right? R1 plus RQ and so on. This is sort of the formula we use. But then in this instance, we only have one resistor in series. So we're just going to have 3.5 ohms. And then now, let's go ahead and find the resistance in parallel. We're going to have 1 divided by RP being equals to 1 divided by R1 plus 1 divided by R2 plus 1 divided by R3 and so on. So we're going to have 1 divided by RP being equals to 1 divided by R1. So the resistors in parallel, this 10 ohm resistor is in parallel with this 30 ohm resistor. Why am I saying so? I'm saying so because the current flows from the positive terminal to the negative terminal. So when the current is flowing at this point, it divides. A proportion of the current comes to this path and another proportion of the current comes to this path. So that is why we're saying that those two resistors are in parallel with each other. So we're going to have 1 divided by 10 plus 1 divided by 30. So RP is equals to 1 divided by 10 plus 1 divided by 30 to the minus 1. If you put that in your calculator, you should get 7.5 ohms. So there we go. We have RP. The internal resistance is given to us right here is 0.6 ohm. So that is to say that RT, the total resistance, will be equals to the resistance in series, which is 3.5, plus the resistance in parallel, which is 7.5. And then lastly, the internal resistance, which is 0.6. You add all that and you'll get 11.6 ohms. And that is the total resistance of our circuit, including the battery. Let's move to 7.1.2. 7.1.2. Let's find the current measured by ammeter A2. Let me just remove these lines so that we can have a bit of clarity. We're looking for the current in this ammeter A2. We're looking for the current in this ammeter A2. So what are we looking for? We're looking for the current. It will be quite easy to find the current if we had the voltage and the resistance, right? But it seems like we have the resistance. There's a heater there with a resistance of 10 ohms. So our resistance is covered. We know that it is equals to 10 ohms. What we can actually do here, we have VT. We have the total voltage, right? And then we have the total resistance. We can find the total current. And then by finding the total current, we can then find the VP. So let's go ahead and say that VT is equals to IT multiplied by RT. The total voltage is equals to the total current multiplied by the total resistance. The total voltage, that is 24 volts. And then the total current, it's what we are interested in, right? And then the total resistance, we calculated it to be 11.6. So IT will just be, so now it's just a matter of saying 24 divided by 11.6, which is equals to 2.069 ampere. So right, there we go. We have IT. Now that we have IT is just taking us a step closer to our answer. We're not looking for IT. We're looking for the reading on A2, and A2 doesn't read IT. So we can say that VP is equals to IT multiplied by RP. If you use this formula, you're going to be able to find the voltage that the heater experiences, or the total voltage on that path, that is. So VP will be equals to 2.069 multiplied by RP. I think RP is supposed to be 7.5. RP is supposed to be 7.5. And if you put that in your calculator, you should get 15.53 volts. So now we have VP. Let's go back to our initial information. Now we have VP. We can say that this V here is equals to 15.53 volts. So now we can go ahead and find our current, because we have VP. We're going to say that the current on that path will be equals to VP divided by the resistance on that path. So VP, that is 15.53, and then the total resistance on that path, it is 10 ohm. So it's easy to see now that the current there on that path should be 1.55 amperes. And now we have answered 7.1.2. 7.2, the variable resistor is now adjusted to have an even higher resistance value. So the resistance of the variable resistor is increased. So we no longer have 3.5 here. We probably have 10 or something, whatever number is greater than 3.5. The question is saying, how will this affect the power dissipated by the heater? Right, only increase, decrease, or remain the same. So what is the equation for power again? Power is equals to I squared multiplied by R. So what is going to happen when the resistance increases for the entire circuit? When the resistance increases, the current is going to go down. If the current goes down and P is directly proportional to I squared, then the power should also go down. It should decrease. So the answer to 7.2 should be decreases, as we can clearly see from our equations. Let's perform an experiment to determine the internal resistance R of a battery. They use a variable resistor as the external resistance, as shown in the diagram below. Yeah, you can see the setup there. And these are the results of the experiment. We have experiment 1, 2, 3, 4, and 5. And the first question, 8.1, is saying, let's use the information in the table above to plot a graph of potential difference versus current. Use the graph paper supplied at the end of the question paper. We need V external versus current. As you can see, we have the potential difference on the y-axis and we have the current on the x-axis. The collaboration on both axes will earn you a mark. If you include all 5 points, you get another mark. If you have a best line of fit, you have another mark. And the last mark is for a negative gradient. Your graph needs to be sloping down. As you can see here, that when the current is increasing, the potential difference is decreasing. The question that really interests me here is 8.2.1. Let's look at 8.2.1. Use the graph to determine the following: the EMF of the battery. So the graph is coming from this information in our table, right? But before we can determine the EMF of the battery in 8.2.1 or the internal resistance in 8.2.2, we actually need an equation for that graph. It is V external versus current, right? But we know fully well that EMF is equals to V external plus V internal. We need V external to be the subject of our formula, right? So we can say that V external is equals to EMF minus V internal. So V external will be equals to minus V internal plus EMF. But we know fully well, beyond reasonable doubt, right, that V internal is equals to I multiplied by the internal resistance. So if we substitute that in place of V internal, then we're going to have minus the current multiplied by the resistance plus EMF. So now you can see the equation we have for graph. It will be easy to determine the EMF and to determine the internal resistance. So let's start with the EMF. Obviously, you can see here from the equation that when the current is equals to 0, V external is equals to EMF. So if you come here to your graph, when the current is equals to 0, V external will be your EMF. So we can go ahead and say that EMF is equals to 1.5 volts and 8.2.2. Saying let's find the internal resistance of the battery. Use an equation to justify the method used. So which equation are we supposed to use? We have already deduced that V external is equals to I multiplied by R plus EMF. It's easy to see that V external is our Y, and then our current is X. So our gradient should be R, right? Plus EMF, which is C. To find the gradient, we actually have to calculate the gradient of the graph using the 5 experiments we have. So the gradient is equals to Y2 minus Y1 divided by X2 minus X1. So let's go and pick 2 points from the 5 data points we have. So we can take this point and this point. So this will be our second point, and this will be our first point. Potential difference is our Y. So we're going to have 1,15 minus 1.5 divided by the current corresponding to 1.15 volts. That is 229. But it's not just 229. Look, we have this M here. We need to be aware of that. So it's 229 multiplied by 10 to the minus 3, and then minus the current that corresponds to 1.5 volts, which is equals to 0, right? And then if you put that in your calculator, you're going to get minus 1.53. So our internal resistance is just equals to 1.53 ohms. And that is the answer to 8.2.2. Let's look at 8.3 real quick. A conducting wire of negligible resistance is connected between the points X and Y. Before we even continue reading, let's just go ahead and connect those 2 points so that we can see with clarity what is going to happen to our circuit. So there we go. What does the equation say? How does this affect the temperature of the battery? Write down only increase, decrease, or remain the same. Explain your answer. It is going to increase. It's going to increase. Let's talk about why that is the case. So when you connect X and Y, you no longer have external resistance. Right? Because the current is just gonna take this path. It's not gonna go to that rheostat there. It's not gonna go to our variable resistor. It's just gonna take this path. So what are we saying? We're saying that the resistance is gonna decrease. The external resistance is gonna decrease. It's actually gonna go to 0. And then when the external resistance decreases, what is gonna happen to the current? The current is going to increase. And then we know that R, our internal resistance, is constant. Our internal resistance is constant. So if our internal resistance is constant and the current is increased, then V internal increases. And then V internal increasing is the reason why the temperature of our battery is actually going to increase. Describe the energy change that occurs in a DC motor. So for all motors, we have electrical energy to mechanical energy as our energy convention. And then for all generators, it is the other way around. We have mechanical energy to electrical energy. So since here we have a DC motor, our answer is just supposed to be electrical energy to mechanical energy. 9.2. Let's explain the term DC. DC standing for direct current is that current that keeps flowing in one direction. So current that keeps flowing in one direction. And then if the question was based on an AC model and we would need to explain what AC means, we would say is the current that alternates, it changes direction. 9.3, in which direction will the conventional current in the coil flow? Right, only from P to Q or from Q to P. We have a motto. For all motors, we use the left hand rule. And then for all generators, we use the right hand rule. For the left hand rule to work, you need to put your thumb, your index finger, and your middle finger 90 degrees to each other. And then with your index finger, your pointing finger, you point from north to south. Right. And then if you do that, your thumb is going to be pointing up if they are indeed at right angle with each other. And then your middle finger will be pointing from Q to P. And then this middle finger that is pointing from Q to P is the direction of the current. So the answer to 9.3 is Q to P. If it was a DC generator, we would be using the right hand rule. We will do the same thing, but now using the right hand. On motors, we use the left hand. Right. 9.4. Explain the change that needs to be made for this motor to be an AC motor. So without being told that this is a DC motor, we can tell by the presence of this split ring. We have these split rings right here. So if you want to change this DC motor to an AC motor, we have to replace that split ring. We have to replace the split ring with slip rings. Don't confuse the two. For DC, we have split ring, and for AC, we have slip rings. Right. And 9.5. Let's look at 9.5 and do some calculation. A heater level 2000 watts, 220 volts and 50 hertz is connected to an AC circuit. Calculate the maximum current that flows through the heater. Right. So we have the power average given to us as 2000 watts. And then we have VRMS, which is 220 volts. And in order to find the maximum current, we will need IRMS first. Why am I deciding that this voltage that is given is VRMS and not Vmax? How do I know that it is VRMS and not Vmax? It is because this heater is connected to an AC. When an appliance is connected to AC, the current is IRMS and the voltage is VRMS. You should put that in mind so that you know what to do the next time you get a question like this. So now we can say that the P average will be equals to VRMS multiplied by IRMS. Nothing new, because we know from electricity that the power can be equal to the voltage multiplied by the current. Nothing surprising there. So the power average, that is 2000 watts, VRMS just 220 multiplied by IRMS. We just divide both sides by 220 and get that IRMS is equals to 9.09 ampere. Another way of finding IRMS is by saying that IRMS is equals to Imax divided by square root of 2. So you can see here what we have to do now. We're going to say that Imax is equals to IRMS multiplied by square root of 2. So we have 9.09 multiplied by the square root of 2. If you put that in your calculator, you should get 12.86 ampere. The minimum frequency of light needed to emit electrons from a certain metal surface. That's what we call threshold frequency. The answer to 10.1. Let's look at 10.2.1. Let's calculate the work function of cesium. Let's calculate the work function of cesium. Let's go through our information and see what we have. How can we potentially calculate the work function of cesium? So we have a photoelectric cell which is connected in a circuit. The lowest frequency of light that will emit electrons from its cesium surface is 5.1 times 10 to the 14 hertz. So we have the threshold frequency, which is equals to 5.1 times 10 to the power 14 hertz. Right. And then we can calculate the work function using the threshold frequency, because the work function is equals to Planck's constant multiplied by the threshold frequency. So this will be equals to H. Planck's constant obviously is a constant, as the name says. It is 6.63 times 10 to the minus 34 multiplied by the threshold frequency, which is 5.1 times 10 to the 14, and this is equals to 3.38 times 10 to the minus 19 joules. We have our work function. This is the minimum amount of energy required for an electron to be emitted. 10.2.2 we're calculating the amount of energy carried by the incident photons of violet light. So we have violet light of wavelength 400 nanometers that is incident on our cesium surface. So the amount of energy, if you are given a wavelength, will be equals to Planck's constant multiplied by the speed of light divided by the wavelength. If you're given the frequency, then it's just Planck's constant multiplied by the frequency. But I'm sure you know that. Again, Planck's constant, that is 6.63 times 10 to the minus 34 multiplied by C, which is speed of light, 3 times 10 to the power 8 divided by the wavelength of the incident light of the violet light, which is 400 times 10 to the minus 9. Now it's just a matter of putting that in your calculator to get 4.97 times 10 to the minus 19 joules, to the minus 19 joules. Let me just write that again, to the power minus 19 joules. So let me show you something. This is the amount of energy from the light that is incident on our surface, and then this is the amount of energy that is required. So you can see that the amount of energy that is incident is greater than the amount of energy that is required. So when those photons are ejected from the surface, they're going to have a kinetic energy. They're going to have some form of kinetic energy. Right, 10.2.3, the maximum kinetic energy of the photoelectrons emitted from the cesium surface when violet light shines on it. So now we actually need that kinetic energy, which I was talking about in 10.2.2. Well, our energy is equals to H multiplied by the frequency, of which the frequency can be C divided by wavelength. But then at the same time, our energy is equals to the work function plus EK max, plus EK max. So what I've realized is that some examiners, if you omit these max here on your EK, you actually lose a mark. So yeah, be aware of that and not lose mark unnecessarily. So in our equation, we have the energy of the incident light, and then we have the work function of our metal surface. Now we need EK max. It's just a matter of direct substitution and making EK max the subject of the formula, solving for X, basically. Easy max. So EK, not EK max, but then the energy is equals to 4.97 times 10 to the minus 19. This will be equals to the work function, which is 3.38 times 10 to the minus 19 plus EK max. Plus EK max. For the faint-hearted ones, we just take in this term to the left-hand side and we are done with our equations, right? And then if you subtract 3.38 times 10 to the minus 19 from 4.97 times 10 to the minus 19, you're going to get EK max. So we have EK max being equals to 1.59. 1.59 times 10 to the minus 19 joules. So that is the maximum kinetic energy of the electrons that are being emitted from the cesium metal surface when violet light is incident.